Hello. Today, together we will read a few handwritten number in PNG file. Then we'll apply an AI machine learning model (CNN), that's convolution neural network, to predict those number. We'll leverage on Keras and popular dataset MNIST. And then to stack a few layers in the model, then we'll instantiate the CNN model, then compile, and then we'll check on the accuracy and loss for both the training and validation sets. Then the program will read a few PNG files with the handwritten numbers in it, and then we will check on those numbers. Okay, without much further ado, let's begin. Okay, I had wanted to write the codes line by line and to show you the whole thing, but I realized that this part of the codes take a lot of times to run. So in fact, I've written the full code. I'm just walking through the codes now with you. Okay, as usual, I'll write the title first and also the who's the author and the date. Then I save it as a file here with the file name predict handwritten number. So that's what I've done for a start. Okay, then um, standard. The first cell is always libraries. I do all the imports here. So OS, CV2, Keras, NumPy, and Matplotlib. I don't think I need OS. Do I need OS here? Okay, ignore this OS for now. Okay, then the start of the code is actually in cell 2. So we'll load the data sets into the X train, Y train, X test, and Y test as here in this format. So Keras datasets MNIST dot load data. So it will the data will fit into all these variables. So as usual, my practice, the X is always a big cap. X train is X is the big cap, and X test the X is always capital letter too. Then we scale the images from 0 to 1 range. So this is the code for that. So we cast it into float 32 and we divide it by 255. Okay. So the next part here is to make sure images have the shape 28 by 28. 1 represents grayscale. So X train, this is the code. MP dot expand dims, so X train minus 1 here. Okay. Then we print. So as you can see, this is the number of data sets counts. So all 60,000 for the train, the X train and Y train, and this is the length, width, and this is the one. Ones means grayscale. There's no so if you have an RGB, then this should be a tree. So Y train shape is a 60,000. So test is 10,000 and 10,000 data sets. So 60,000 training samples, 10,000 test samples. Okay, why there's a division by 255 scales the pixel to the range 0 and 1. This makes it easier for the neural networks to learn since the inputs are on a consistent scale. So it's also reducing the risk of numerical instability or slow convergence. Okay, neural networks performs computations in floating point decision. So converting to float 32, this one here, ensures compatibility and enables the division to produce normalized values with decimals. And float 32 is widely used in deep learning because it balances the precisions and memory usage effectively. So we rarely use float 64. Oh, sorry, where is it? Okay, I think it's somewhere. Okay, we rarely use float 64. Uh, Mainly because it will consume more memory and can slow down computations. Okay, so six this year is the same as 60,000, 28, 28, 1. So it represents 60,000 images with dimensions of 28 by 28, and 1 represents grayscale. Okay, neural networks, particularly convolutional neural networks, expect input images to include in the channel dimension explicitly. This is the one. The input shape must be specified as height, width, and channels. So in this case, it's 28, 28, 1. Okay, our model parameters. Number of classes, num classes equals to 10 because it's the output is is either either one of the values from 0 to 9. So that's 10. Then the shape is 28 by 28 and 1. Okay, so this is the model. So we need to stack a few layers around here. So these layers actually can play around and changing of different values and the sequence and see how it affects the results. So I'm not saying this is the best, but I think I'm comfortable that we came out with this. Okay, so the first one is to specify the shape. So we have input the we have defined the input shape here, 28 by 28 and 1. So the formula. So we input the shape here. Okay, the variable shape. So we just input here. Then the first convolutional block, we have the CONV2D. So applies a 64 feature detectors of size 3 and 3, 3 by 3. So to extract the features like edges or textures with activation code ReLU. So we have two of these here. Then we do a max pooling 2D here. So the max pooling reduce the size of the feature map. So it's actually a downsampling by taking the maximum value in 2 by 2 regions. This makes the model faster and less prone to overfitting. Okay, then this is our second convolutional block. So similar to the first, but this time with 128 filters. This means the model is learning more complex features like shape and patterns. So this is the two lines of codes here. So this is actually this is my second trial. I'm just doing it just to see how it goes. So I'm just putting it with different value 32, 32, and it ran. So I just keep it just for me my own test. And there's also a global average pooling 2D. So it converts the feature maps, the spatial information into a single vector per map by averaging. This reduces the number of parameters compared to a fully connected layer, making the model lightweight. So this is the one. Okay, so this one is the drop out. So 50% of the weights randomly sets 50% of the weights to 0 during training. So it prevents overfitting or by ensuring the model doesn't rely too heavily on specific neurons. Okay, so this is the last layer. As standard, we define the num classes. That's 10. That's the output. So here, so activation code now is softmax. Okay, now we in the next cell is we need to compile it. So the loss we assign it to sparse categorical cross entropy. Then the optimizer we specify as Adams, and the matrix same sparse categorical accuracy. Sorry, this sparse categorical accuracy. So then the next we define the batch size, that's 128, and the epoch 30. So we also define callbacks here. So there's this is the callback codes here. So we do a feed with the X train and Y train. Then we define the batch size and the epoch here. And we also have a validation data set. That's a split of 0.15. So callbacks is this one. So it ran. So it stopped at around 7. So okay, here. Before this, actually, before I input this to, it stopped at 11. It stopped at around 11. My just own testing. Okay. So we have also printed out the score to evaluate the model. So the score is 99.2%, which is not bad. So and this part of the code, uh, there's a function where you can save it so that it becomes persistent, and you can load it back maybe a few days later or sometime later and to a variable. Let's call it model or model one or model with a date, uh, to make it easier for you to identify. Okay, then now this is the training and validation accuracy plot, which I kind of like it. So as you can see here, it started, or this is the accuracy. Both are very high. So for the this is the training accuracy. It starts from the low, then it spike up, then it continue to grow, and it ends here. So for the validation accuracy, it's from this point already quite high. So it ends somewhere here, quite close. In fact, when previously without these two codes, this is much closer. That's my observation. But there's some gaps here. Okay, you can see here. So the validation accuracy is 0.99, which is this one, 0.991, 0.992. But for the accuracy, training accuracy is 0.97, so it's slightly below. Okay, 95, 96, 97 should be somewhere here. Okay, then we also then there's also a plot on the loss, training and validation loss. So from here you can see for the training loss from the very high, from the high, then it start to drop as it run the epoch. It starts to drop, and this one is also there's a gradual drop for validation loss. Okay, so they actually if counts back to quite the same, although there's still a difference here, but actually it goes down to the same, pointing to the same directions. Okay, so let's see this value here. So the value loss is 0.04 for validation set, and for the training set it is 0.08. Okay, so the loss, uh, validation loss, I think is better. Let me check. Yes, validation loss is better. We need to get as low as it can. Okay, but still, this is something good to see because it's going downwards and gradually going downwards here. So it's healthy in that sense. So this is a prediction statement here. Prediction is equals to model.predict. Then we put in the x test. Okay, this is just a test. So the variable index we just assume I'll just randomly put a 0. So and it printed out a 7. So the data set at 0 index is a 7. So we also plotted out the x test with the index, and it shows a 7. Okay, uh, this is just a test. So again, this is the function. So it's just to put in the file with the path. Then we then it return a predicted number. So so this is just a test for the 1, but it printed out 3. Okay, so there's a learning or the handwritten number is not the system cannot accurately predict it for this case. Uh, so I've also put the list of in a list the file name with the corresponding number, and through a loop it printed out the predicted number. So let's see. So for 0, uh, it gives a 0. That's correct. For 0, the second different number, it gives a 2. That's incorrect. And this 0 is correct. This 1, it gives a 3. It predicts a 3. That's incorrect. 1, it predicts the 1. That's correct. This correct, correct, incorrect. So correct, 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 incorrect, correct, correct, incorrect, incorrect, and correct. So how many it got wrong? Uh, 1, 2, 3, 4, 5. So 5 was wrong out of 5 is wrong out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 5 out of 20 mistakes. Not too bad. Actually, we can play around with this here. Can change the values here to make it more probably to improve the performance, or you can change the epoch size, things like that, and to change the epoch. So you need to do both. So play around with this value here and change values here to see how it goes. Okay, let's go into the my file, my number file. Okay, this is the directory. So actually, this is the handwritten number. Let's go to those that are wrong. It could be the the learning set itself, because it my when I read, I understand that they got to the U.S. schools and they get the students to write all the different numbers in thousands. So it could be the way that Asians write numbers and how the uh, students in the West could be different, slightly different, slightly depend on the culture, the way that they write stuffs, the handwriting styles, and things like that. Okay, 7 is correct. 9-1 is wrong. Let's check. This is wrong. Okay, so it could be this part here, things like that. So it's not able to detect a 9. Okay, but the other one is correct. Let's check on 9. Oh, both are wrong. 9, it gives it predicted a 3. So this is also wrong. This I am not sure, but it gave a wrong prediction. So you need to play around with the variables up there. And 8 is correct, 5 is correct, 4 is correct, 3 is correct, 2 is correct, 1 is correct. Number 1 here is different. So let's open up. I have no idea. Okay, let's go to 1A. This is able to predict a 1. So comparing with the, so maybe treated as an I. It's just a one straight line without the how do I move this? So without this part here and this part here. Okay, so this is able to detect. Okay, let's close this. What else? 0 is correct, 0 is correct, 0 is correct. Okay, number 1. Oh, we did the 1. Okay, 1A is correct, 2 is correct, 3 is correct, 4 is wrong, and 4A is correct. So we open up 4. Okay, so this is wrong. Am I right? 4 is wrong. It gives me an 8. And 4A is correct. Oh, because I think earlier is the opposite. I have ran a few times. So earlier is this was wrongly interpreted, and this is correct. But now this is the other way around. Also because I've played around with this part here. Uh, Maybe if I remove these two lines, I'll get that 4 correct. So it's about playing with the parameters to make it, to refine it, to make it more accurate in that sense. Okay, so I think that's about it. Let me check again. Where else? So 4 gives 8, 4A is correct, 5 is correct, 6 is wrong. So we open up 6. 6 is this one, non 6. This it gives me a 5 for some reasons. Okay, so again, need to play around. So in all, I think majority are correct. Just that a few are wrong. I think we somehow we need to uh, refine on this. Okay, that's all that I have for today, and I hope this is fun. It's not difficult to do. You can find this online. You can download the dataset, or you can just simply use this code to load it into the training data and the testing data, and you can start from here. I think there's some tutorials, and also from the learning side, they should have. You can start with that. Okay, then you just play around. It should be very interesting. So this is CNN. We have touched previously. We have touched on ANN. ANN is just a prediction, classification prediction. Now we have we did something different today. So it's a prediction, reading of numbers, and we have touched on CNN, uh, convolutional neural network. Okay, thank you. I hope you like this, and see you again the next time.